In this lesson, we're going to talk about the mathematics of Fourier transforms in one dimension, and you'll see that it's not really that complicated. In fact, in the coding assignment that will follow this lesson, you will use this math to code your own Fourier and inverse Fourier transforms from scratch, and that really helps demystify all this. As we discussed in the last lesson, a Fourier transform returns an array of complex numbers. So let's quickly review complex numbers to see why the Fourier transform does that and how those complex coefficients can be used. This is a good reference for complex numbers in Wikipedia. Any complex number z has a real part a and an imaginary part b, and then the I is the complex coefficient, which is the square root of -1. So a complex number z can be visually represented as a vector on this diagram that's called the Argand diagram, and the x-axis is the real axis and the y-axis is the imaginary axis. And again, the complex number is just z equals a plus b times I. The vector has both a magnitude as well as a phase angle, which is its angle with respect to the real axis. The magnitude is called r, and the phase angle is called phi, or in modern Greek this is pronounced phi, but we'll refer to the English pronunciation phi. So the magnitude r is obtained by really taking the absolute value of the complex number, which is done by computing the hypotenuse of this triangle, which is the square root of a squared plus b squared. And the phase angle, or phase phi, is simply computed by taking the arctangent of b over a. So we have these two formulas, and basically we understand that any complex number z can be expressed in terms of its magnitude r and phase phi. But we can take it a step further. If we look over here, the real component of the complex number a can be expressed as its magnitude r times the cosine of phi. So a is r times the cosine of phi, and b, which is the imaginary component, is r times the sine of phi. Okay? So a is r times cosine of phi, b is r times the sine of phi. And if we were to substitute these values in the original equation for the complex number, we'll end up with this. So any complex number, it can be expressed in terms of its magnitude and phase by this formula, which is called the polar form of the complex number. Now we get to the all-important Euler's formula, and without proof, we'll present this for every angle theta, not just the phase angle phi, but any angle. If you take the cosine of that angle and the sine of that angle, and you multiply this by the complex coefficient and sum them, that equation is equal to e exponentiated to I times phi. Okay, so clearly this looks the same as that. So combining these two formulas, the polar form and the Euler's formula, we end up with this, which means that any complex number z can be expressed as an exponential function using its magnitude and phase. And this is the form that is used in the Fourier transform. All right, so now let's move on to the Fourier transform. We're really interested in the discrete Fourier transform because we're dealing with a signal that may be continuous in nature, but we have sampled it at discrete intervals, and more importantly, for image analysis, we're dealing with pixels, which are discrete, as we'll get to later. So the formula for the discrete Fourier transform is this, and we'll talk about that. There is a continuous form of Fourier transform that just uses integrals instead of sums, but it looks very, very similar to this. So let's talk about this. We start with a signal x that is composed of n samples. Okay, each sample point is x0, x1, all the way to x to the n, x sub n minus 1. And once we take the Fourier transform of that signal x, we end up with another array. This array is an array of complex numbers, big x0, big x1, big xn minus 1, but it has the same length as the original signal array. So it has length n. Let's look at this formula. X sub n, little x sub n, is just one sample in our signal. That is the value of the signal at one time point. We multiply that by this exponential function, and then we sum over all samplers from x sub 0 to x sub n minus 1. And that gives us the Fourier coefficient at a particular index, 0 or 1 or k or n minus 1. Okay? So there are two important implications here. The first is that, look at this. This is an exponential function of the same form as this. And this is a coefficient like this. So Euler tells us that this is a complex number like z. When you sum n complex numbers together, you end up with a complex number. This is why the Fourier coefficients are complex numbers, because of this formula. The second important point is that there is not a one-to-one correspondence between the sample points, x0, x1, little ones, and the Fourier coefficients, big x0, big x1, even though both arrays are the same length. For each individual Fourier coefficient, x sub k, we are looking at the entire signal. We are summing up x sub n over the entire length of the signal. And that's a really important concept that we need to remember when we get into interpreting the magnitude spectra for images. The last thing to note about this is that after we've gone through this summation, that is after we have looped over all sample points to create the sum, we've only computed a single Fourier coefficient in this array. In order to compute all of the Fourier coefficients and come up with a complete Fourier transform, we have to repeat this summation n times. So the time complexity of computing the Fourier transform in this way is n squared. One for computing this sum and another loop for computing all of the coefficients in the Fourier transform array. Now we can simplify this, or rather just create a shorthand for representing this Fourier formula. What we can say is we can define a complex coefficient that we call omega that's equal to e to the exponentiated to negative I times 2 pi divided by n. This is all a constant. N is a constant, pi is a constant, I is a constant. This whole thing is a constant. It has a name. It's called the primitive nth root of unity. So if we define omega in this way and substitute it in this equation, that kind of simplifies our equation to this. And this is the form of one-dimensional Fourier transform that you will see everywhere. And this is the form that helps us code it. And then we look at the inverse Fourier transform. It has a very, very similar form to the forward transform. The only difference is that here we have positive kn as the exponent, here we have negative kn, and in addition, once we have computed the sum in the inverse Fourier transform, we normalize it by dividing by the total number of samples. So once we have computed the, all of the Fourier coefficients x sub k, we can use them, we can use each of these complex numbers to extract the magnitude and frequency at a particular index k. And that's really simple. We already talked about the magnitude of a complex number just being its absolute value, which is also equal to the square root of a squared plus b squared, the real and imaginary parts of the complex number. And for that, we can simply use the numpy's absolute value function. And to extract the frequency at each of these indices is just the index k of x sub k. It's just that we need to normalize that index by multiplying it by the sampling frequency and dividing it by the number of samples to end up with the frequency at index k. And the SciPy function that we have talked about in the previous lesson is a very simple function that achieves exactly that. There's one last detail. It turns out that the mathematics work in such a way that we end up with both positive frequencies and negative frequencies. That is, there is a mirror image of this diagram that has all of these spectra in the negative frequency domain as well. But we're not interested in the negative frequencies, so we just plot the positive frequencies in our frequency spectrum. And remembering this is also really important when we talk about magnitude spectra in the 2D Fourier transforms for images and why they look the way they do. So now that we have some understanding of the mathematics, we're going to go ahead and build our own Fourier and inverse Fourier transforms using these formulas.